Good morning, students. In the previous lecture, we have seen the relationship between current and current density, right? Yes, how we define current? The rate of flow of charges, dq by dt. But we have considered the rate of flow of positive charges, right? Okay. Then current density, it is represented by J, and it is given by current passing through unit surface area. All these things we have seen. Then relationship between I and J. I is equal to surface integral of J dot ds. This we have seen. If it is a closed surface, we will put a circle over it, right? Closed surface integral of J dot ds. This we have seen. Then yes, what is the relationship between the current density J and the volume charge density? If the volume charge moves with certain velocity, I will get current density. So the charges in motion constitutes current, right? Using that we will write so rho v into the velocity of the volume charge, right? The charges in motion constitutes current, right? And continuity equation of current, right? So this we call it as integral form of continuity equation of current. Then differential form, also called as point form of continuity equation of current, del dot of J is equal to, it is the rate of decrease of the charges within the given volume or surface, closed surface. So dou by dou t of rho v. So this minus sign indicates the depletion of charges or the decrease of the charges within the considered closed surface or volume, right? This we call it as point form of continuity equation of current. All these things we have studied, and we have solved few numericals based on that, right? Okay, in today's lecture, what we are going to cover, metallic conductors we'll see. Then already we are familiar with the Ohm's law, usual form of Ohm's law. We will see the point form of Ohm's law. What is that? Then next we'll solve few numericals based on that. Then we'll see the conductor properties and the boundary conditions, and we'll have a look at the derivation, that is boundary conditions between conductor and free space, right? If time permits, we'll solve few numericals. Yes. Before studying the metallic conductors, we have to differentiate between conductor, insulator, and semiconductor. This is the energy band diagram of the conductor, insulator, and semiconductor. So the two bands are highlighted here, the valence band and the conduction band, right? So you can observe in case of conductors, almost the valence band and conduction band are overlapping. If small amount of energy is provided for the electrons present in the valence band in the form of heat or light or electric field, they will jump to the conduction band, and those we call it as the free electrons. Those are responsible for conduction in the metallic conductors, right? Then okay, conductors are those which are having higher conductivity, right? We can call them as they are having higher conductivity. Then insulators are those materials which are having lesser conductivity or no conductivity at all, right? Okay, you can observe the large difference or energy gap between the valence band and the conduction band. Okay, if I provide the external energy to the electrons present in the valence band either in the form of heat, light, or electric field, what will happen? They will try to jump to the conduction band, but the temperature will increase in such a way that the insulator will break down. It will melt, the insulator will break down. So insulators are not used for conduction, right? So insulators are those materials which are having no conductivity or lesser conductivity, we can say, right? Then semiconductor, you can observe the difference between the energy gap between the valence band and the conduction band, right? The energy gap is very less. So how to define semiconductors? Semiconductors are those materials which are having conductivity in between those of conductors and insulators, right? So every material has their own role to play. So we'll concentrate only on conductors here, right? And these are the energy band structure at the temperature of 0 degree Kelvin, right? Okay, we will concentrate only on the metallic conductors. Okay, we will consider the conductor. Okay, let me take the piece of wire. If I conductor means just wires, your normal wires, right? So they are in the cylindrical shape, right? Cylindrical structure, right? Piece of wire I have taken having length L, something like that, right? It can be of any shape, but usually most of the times we consider cylindrical structure or shape, because the usual wires what we are using for our homes or offices, they will be cylindrical in nature, right? Copper wire, right? Okay, we'll consider this only with which we are familiar. Consider the conductor which is under the influence of the field, right? The field within the conductor, let me take the electric field is E. Okay, we are applying the field as some free electrons are there which is responsible for conduction, right? So those free electrons, the charge on the free electron is minus e. The charge q is minus e. This is the charge of the electrons, right? And valence electrons or free electrons move under the influence of electric field. Yes, there is electric field. The valence electrons or free electrons present in the metallic conductor, they will move under the influence of the electric field, right? Always they will move from higher potential area to the lower potential area, right? If the field direction is in this direction, right? The free electrons will move as per the under the influence of the electric field from higher potential area to lower potential area, right? Then what is the force experienced by the electrons within the field, right? So we know the definition of electric field intensity, the force acting on the unit positive test charge. But if I want to find out the force acting on the free electrons or charges, then F is equal to Q into E, right? So this is Q into E. F is equal to Q, Q into E. Sorry, Q into E. So Q, what is Q? The charge on the electrons is minus E and E as it is, right? Q into E. The charge on the electron is minus E. So Q into E. This is the force experienced by the valence electrons or free electrons, right? Then what is this drift velocity? Before proceeding, I will tell. Just observe here. Yes, there are free electrons which are responsible for conduction in the metallic conductors. What they will accelerate and they will move with certain velocity. While moving, what they will hit with the lattice structure of the atoms present in the metallic conductor, and more number of free electrons are generated. So the density of the free electrons will increase and they will move with a common average velocity. That common average velocity we call it as drift velocity, right? That common average velocity of the electrons in the metallic conductors, we call it as drift velocity, and it is given by Vd vector. Vd vector is equal to minus mu e into E vector. So what is this mu e? Mobility of electrons. It depends, mobility of the electron is constant and it depends whether it is aluminum or copper, right, or silver, right? So the mobility of the electrons will change based whether it is the aluminum or copper or silver, based on the material. So the mobility of the electrons will change. With the mobility of electrons in aluminum is different, in copper it is different, in silver it is different, right? Okay, the drift velocity and electric field intensity are directly proportional, right? So if the electric field intensity increases, the drift velocity, the right, also increases, and the proportionality constant is mu e minus mu e. Mu e represents the mobility of the electrons, right? And one more thing, the electron velocity is in a direction opposite to the field E. The field, if E is in this direction, the mobility of the electrons will be opposite in the direction, because we are considering the conventional current, right? So the flow of actual current or the flow of electrons will be opposite to the field in this direction, right? The flow of electrons will be in the opposite direction. Please keep this in the mind, right? Then yes, so due to this drift velocity, what will happen? The electrons will be moving with certain velocity, that is common average velocity, drift velocity. And if they are moving in the metallic conductor, it will lead to a rise in the temperature, right? If it is within the permissible limits, it is fine. If the temperature goes on rising, there is a chance that the metallic conductor will melt. The conductor will melt. So we should take care of that. Means either the heat should be dissipated in the form of radiation, right? That should be taken care. Okay, so these are the few relationships you should remember, that's all, right? Okay, then we know this relationship. The motion of charges constitutes current rho v into v. This is the velocity of the charge, rho v into v. The motion of charges constitutes the current, J equal to rho v into v. This we are familiar. Then what is the drift? This is drift velocity, so minus mu v into e. I will substitute here, minus mu v into e. Then what is this rho v? It is, here the charges are free electrons, right? So free electrons, the volume charge density, here it is free electron charge density, rho e. Instead of rho v, I will write it as rho e. This rho e is nothing but free electron charge density, right? So substitute for v, v is minus mu v into e, minus mu v into e. Then what is this rho v? Rho v is nothing but free electron charge density, right? Here the volume charges are electrons, so we will free electron charge density, we call it as rho e. So it is also constant, it will be given, right? Then finally I can write this as J equal to sigma E. Sigma, what is this sigma? It is conductivity of the material, conductivity of the conductor or conductivity of the material, sigma. And sigma is equal to minus the free electron charge density rho E into mu V. So it is given here, rho E is equal to minus rho e into mu e sigma. So this is conductivity of the material or conductor, right? So J equal to sigma e. This equation we call it as point form of Ohm's law. So you are familiar with the Ohm's law. V equal to V is directly side V equal to IR. So this is the macroscopic form of Ohm's law. Usual form or macroscopic. Usual form or macroscopic. Macroscopic form of Ohm's law. This you are familiar, right? So here J equal to sigma E. Here this we call it as point form of Ohm's law. Here we define the relationship between voltage and current in the form of the proportionality constant, the resistance here. But here you can observe here we try to relate between the current density J and the electric field intensity E in terms of the proportionality constant sigma, the conductivity. Here we conductivity and resistivity, they are inversely proportional. Sigma and resistance R, sigma and R, they are inversely proportional. So they are exactly opposite, conductivity and resistivity, right? So here we express or we relate the current density and the electric field intensity, right? If the conductivity increases, the current density increases, right? If the conductivity of the material decreases, the current density decreases. They are directly proportional. And with respect to field, yes, if the intensity of the field is more, the current density increases. If the intensity of the field is less, the current density decreases. So this equation J equal to sigma E, we call it as point form of Ohm's law, where sigma is conductivity of the material or metallic conductor, right? Okay, you have to remember these equations. The drift velocity, it depends on the field, and the mobility of the electrons minus mu v into E. You have to remember while solving the problem, this will be helpful. Then J, what is this? You can substitute, we know the relationship, you can substitute J equal to sigma E. What is sigma? Sigma is equal to the free electron charge density rho E into mu V minus. You have to remember these three equations, this and this, right? Okay. Already you are familiar with the usual form of Ohm's law. Point form of Ohm's law we have seen J equal to sigma E. So already you are familiar, we'll see the usual form of Ohm's law. Okay, this is the cylindrical conductor, right, of length L. And we will assume that the current density J and the electric field intensity E are uniform throughout this metallic conductor. So the current density within the metallic conductor and the electric field, they are uniform, right? We are assuming it, right? Then let me take this cross section, right? The area, and this, there are two ends. This is one end of the conductor and this is another end of the conductor. Let me call this as B and let me call this as A, right? So this one end as B and another end as A, right? Okay, let me consider this surface area, right? And what is the current here? We know the relationship between what is the current density? J is equal to current passing through unit surface area. We know this. Then what is current I? I is equal to J into S, right? So the total amount of current entering is J into S because both J and E are uniform here, right? So simply without looking at the vectors, I can write I is equal to J into S. And we know the integral form of the continuity equation I is equal to surface integral of J dot ds. So in terms of magnitude, so since, right, if I consider this surface, the current is same. If I consider another surface here the current flowing through this is same because J and E are uniform. If I consider the end, so the current is same. So what we are doing, just it is multiplication of the current density J and the surface area J into S, that's all. Is it fine? So this integration is removed, J into the surface area, whatever the surface area we are taking here. So J into S I can write. I hope you are getting I is equal to J into S. Okay. Then next, the potential difference between the two ends. I have one end of the conductor here, let me call it as B, and I have another end of the conductor here, let me call it as A. So we know the potential difference between the two ends, right? So VAB. So final position and this is initial position, right? So A is final position and B is initial position. So minus, we know the definition of potential difference, minus integration of E dot dl, initial position to final position, B to A. Okay, just observe here E, then integration I am left. So E is taken out, E is because E is uniform, so take it out. So E vector. So what I am left out, integration from B to A dl. Is it fine? B to A. So upper limit minus lower limit. What I will be getting? L upper limit L A L minus L L A B can I write? But this minus sign is there. I can write yes. Upper limit minus lower limit. What I will be getting? L A minus L B or distance from A to B. So this the total this will give me the distance from L A B. Actually L B A will come. So this minus sign is taken care and it will be I can write it as L A B. Is it fine? The total length of the conductor or simply L also I can write, no problem. So this is VAB. Then I want to remove this vector notation. Simply I can write V is equal to E into L, right? Because E is uniform, right? And the length L, total L. But what about E? E is equal to V by L also I can write. This is by definition. We know the units volt per meter, right? So E is equal to V by L. V for volts and L for meters. Volt per meter. You can remember like this, right? V equal to EL or E is equal to V by L. Then next we'll try to establish, because still the usual form of Ohm's law we have to come across. We'll see next. We got V, right? We got I. Then what about R? We'll see. So we from this we know I is equal to JS. J is equal to what? I by S. Then we know that J equal to sigma E also. This is point form of Ohm's law. J equal to sigma E, right? We are not taking the vectors here, just magnitudes. J equal to sigma E. Then sigma as it is. What is E? E is equal to V by L. So relate these two equations, this and this, right? So what we are getting? V is equal to what? L into I divided by sigma S. L into I by sigma S we are getting. So this is the Ohm's law. C equal to V equal to IR. I and this entire thing represents R, right? So V equal to IR, the usual form of Ohm's law, also called as macroscopic form of Ohm's law. This is true for uniform fields because E is uniform throughout that metallic conductor. So what is the value of R here? R is equal to L by sigma S. Means R depends on the length of the conductor. The length of the conductor, then it depends. It is inversely proportional to the conductivity of the material and surface area of the material. If the length of the conductor increases, the resistance increases, right? If the surface area increases, the resistance decreases. They are inversely proportional, right? So as already we have seen, the resistivity and conductivity, they are inversely proportional. If conductivity increases, resistance decreases. If conductivity decreases, the resistance increases. So you remember like this: R is equal to L by sigma S. You have to remember these equations. This, right? Then for non-uniform fields, will not worry. So V equal to IR, R is equal to V by I. We know the potential difference formula, minus integral B to A E dot dl, and I is equal to surface integral of J dot ds, right? J dot ds. What is J? J is equal to sigma E, right? We will not see this. We will not worry much about this. We will leave it. For uniform fields, we will see. We will not worry much about this. Then we'll try to solve this numerical. If any doubts are there, please unmute yourself at that moment and speak to me, right? So that I can address at that moment. Okay, as an example, okay, we'll not take all these things. The determination of resistance of a cylinder. Okay, from here the question starts. Find the resistance of a 1 mile length of the copper wire. Means 16 gauge. So 16 gauge, 18 gauge commercially, right? People will say 16 gauge, 18 gauge, right? Hash 16 means 16 gauge copper wire, right? So find the resistance of a 1 mile length of the 16 gauge copper wire which has a diameter of 0.058 inch. Okay, let me try to draw that cylindrical conductor. Okay, the length of the conductor L, it is 1 mile. L is equal to 1 mile, right? Then diameter of the conductor, the diameter D. So D is equal to how much? 0.0508 inch. Okay, this is given. What is asked? Find the resistance. So we know the formula of resistance. It depends on length of the conductor and inversely proportional to the conductivity of the material and what another thing, surface area. If you remember, R is equal to L by sigma S, right? This equation, right? So length of the conductor, it is given in miles. Then surface area we have to find out. Then sigma will see. Surface area means this one, pi r square, right? We will see this. Okay, one by one. What is L? This is in 1 mile. So we should convert it into L is equal to 1 mile. 1 mile is equal to, just I have given the hint, you should remember. 1 mile is 1.6 kilometer roughly. 1.6 kilometer means 1609 meters. 1609 meters. So convert everything into meters. Then diameter is given. It is in inches. 0.0508 inches. So what is 1 inch? 1 inch is equal to 2.5 centimeter or 0.0254 meters. Right? So I will multiply by, I will convert it into meters. 0.0254. So first convert it into meters. So take the calculator. 0.0508 into 0.0254. So I am getting it as 1.29 into 10 power minus 3 meters. Yes, but what I want, surface area. What is surface area? Yes, right? So this is, let me consider this surface area, pi r square, right? Pi r square. But we have diameter divided by 2 will give me radius. So the radius is d by 2 whole square, right? Diameter divided by 2 will give me the radius. So pi r square, d by 2 whole square. So pi into d is 1.29 into 10 power minus 3 divided by 2 whole square, right? We will calculate this. 1.29 exponential minus 3. So let me put it in the bracket. 1.29 exponential minus 3 square. It's square, right? Into pi. So I am calculating the numerator. Into pi. Into pi. Yes, this is giving me 5 divided by 2. So divided by 2 divided by 2 square. 2 square is nothing but 4. Divided by 4. So I am getting it as 1.3069 into 10 power minus 6. This is surface area in meter square, right? So meter square. So we know everything. Substitute and calculate. R is equal to, L is how much? 1609 meters. Yes. For conductivity of copper, yes, this will be given. No need to remember. Conductivity of copper, sigma. For conductivity of copper is 5.80 into 10 power 7 Siemens per meter. So there is no need to remember. It will be given, right? So sigma is 5.8 into 10 power 7 Siemens per meter into, yes, surface area is 1.3069 into 10 power minus 6. So we will calculate this. 1609 divided by 5.8 exponential 7 exponential, yes, exponential 7 into 1.3069 exponential minus 6. So I am getting it as 21.22 ohms. So R is equal to 21.22 ohms, right? You can check it. So one thing in this problem you have to remember, if it is given in miles, convert it into meters. So 1 mile is equal to roughly 1.6 kilometers, that is 1609 meters. 1 inch equal to 2.54 centimeter, and it is equal to 0.0254 meters, right? Then everything is smooth as usual. So yes, I just here the conductivity of aluminum, copper, silver has been listed here. These are constants. And the mobility of the electron in case of aluminum, copper, silver, it has been listed here, right? These things will be helpful in the future problems, right? That will say it. If any, this will act as a reference for us. Okay, we'll take up few more numericals. Find the magnitude of the current density in a sample of silver which has conductivity sigma is equal to 6.17 into 10 power 7 Siemens per meter, and mobility of electron is this much meter square per volt second, right? If part A, the drift velocity is 1.5 micron meters per second. So, okay, we'll take a part A. Drift velocity Vd is given. So it is how much? 1.5 micron means 10 power minus 6. So 10 power minus 6 meters per second. Okay, drift velocity is given. So this is not a vector, right? Simply magnitude they have given. Then what they have asked, find out the current density J. Then material is silver. and sigma is given. Sigma is 6.17 into 10 power 7. I will not write the units, Siemens per meter, and mu v is given. Mu v is equal to 0.0056 meter square per volt, right? Everything is in meters, so I will not worry. So I am not writing the units. So how to find out? Uh, what is there? How to find out? How to relate this Vd and J? Is there any other means? Drift velocity is given. So these are the set of equations we have to think of. Just have a look at it, which we have to use. Right, mobility is given, fine. J equal to sigma E. What about E? How to find out? All these things we have to worry. So drift velocity, this is given. Mu v is given, I can calculate E. If I know E, I can J equal to sigma E. So I will use this equation, drift velocity. Vd is equal to minus mu v into E, so that I can calculate E, right? So since they are given magnitude, Vd, simply I will not use vectors. Vd is equal to minus mu v into E, magnitude I will take, right? So we will try to use this equation and this equation. Vd is equal to minus mu v, mobility of electrons, electric field. So I am not taking the vector, just I am taking the magnitude. This is one equation, and J equal to sigma E. Just I am taking magnitudes, right? Not the vectors. Okay, fine. I know mu v, I know drift velocity, I can calculate E. First calculate E. So E is equal to Vd. Vd is how much? 1.5 into 10 power minus 6 divided by minus mu v, mobility of electrons, 0.0056. So this will give me E. Is it fine? So we'll calculate 1.5 exponential minus 6 divided by minus 0.0056. I am getting it as minus 2.678 into 10 power minus 4 volt per meter, right? Then I'll substitute here. So J equal to sigma E. J equal to sigma E. What is sigma? 6.17 into 10 power 7 into E minus 2.678. Somewhere I have made a mistake. Please check it. This minus sign is not coming here. But this minus, mobility of electrons, minus mu E. In the formula, whether there is minus, yes, it is there. Yes, minus is there. Mu E, is it fine? J equal to sigma E, that is also fine. Sigma. So Vd, that is fine. Mu V minus mu E. Whether this minus should be taken or not, that is the thing. Mu V 0.0056. They have given it as positive only here. No minus. Let me verify it. We'll calculate. We'll see later. Into 10 power minus 4. Okay. Let me discard this minus at a moment. 6.17 exponential 7 into 2.678 exponential minus 4. So I am getting it as engineering 16.523 into 10 power 3. Current density is ampere meter square. I am getting this 16.5 kilo means 10 power 3. But minus sign, I think for mobility of the electrons, it is minus only, right? Just I have written here. Let me check it. They have given positive only here. Positive only. Silver 0.0056. Maybe with respect to this only, minus this minus mu v. Actually, I should take this sign at a time, I think. Maybe because of that, right? Otherwise everything is fine. So whenever mobility of the electrons will come, we'll assume that it is negative only, because as per this we are getting negative only, right? So this will be plus. We'll see in the next problem, right? Whenever the mobility comes. So this first answer we got it, right? Then part B. I'll get back to you with this, right? Right now you take it as positive, right? Okay. Next, the electric field intensity E. E is given 1 millivolt per meter. 1 milli means 10 power minus 3, 1 millivolt per meter. It is given. So find J. Yes, J equal to sigma E, right? That's all. Very simple. Sigma E. What is sigma? 6.17 into 10 power 7, right? Into 1 milli. 10 power minus 3. Is it fine? So 6.17 into 7 minus 3, 4. 10 power 4. If I want textbook answer, I can write it as 61.7 into 10 power 3, right? 10 power 3 amp per meter square. Sorry, meter square this one. Okay. 61.7 kilo. Kilo means 10 power 3 amp per meter square. Next we'll see the part C. Yes, sample is a cube. Yes, silver, whatever the sample of silver is, it is in the shape of a cube. Right? It is in the shape of a cube. No need to draw it, just I'm drawing it. Right? And the side 2.5 mm meter. 2.5 mm. All the sides 2.5 mm. Right? Then having the voltage of 0.4 millivolt between opposite phases. Let me take this one as phase and the another phase. Two opposite phases. The voltage potential difference between two phases is 0.4 milli. Milli means 10 power minus 3 volt between opposite phases. So calculate J in this case. So how to calculate? Potential difference between two phases is given. We know the sides. We need to calculate J in this case. Let me check it how to calculate, right? Let me try to use the equations here. Uh, can we use this? V equal to EL, right? V equal to EL. Potential difference between two phases, right? V equal to EL is possible here. Uh, V equal to EL. Yes, I know the potential difference V. I know the length. I can calculate E. So yes, I can do it. J equal to sigma E. So we will calculate E from this, right? So yes, we can proceed with this. So we will calculate E here. E is equal to V by L. The potential difference between two phases is this. Let me consider this phase and this phase, right? These two phases is 0.4 into 10 power minus 3. What is the length between the two phases? It is 2.5 mm. 2.5. Sorry. Something, what happened? 2.5 mm. This is not there. 2.5 mm. So 2.5 mm milli means 10 power minus 3. So 10 power minus 3, that will get cancelled. So what is E we are getting? E is equal to 0.4 by 2.5. So I am getting it as 0.16 volt per meter. So let me calculate J. What is sigma E? So what is sigma? 6.17 into 10 power 7. And what is E? 0.16. So we'll calculate J. 6.17 exponential 7 into 0.16. So I am getting it as very huge value. Let me convert it, right? 9.872 into 10 power 6, 10 power 6, right? Amp per meter square. You can check it. 9.9, 9.9 mega means 10 power 6, right? Mega amp per meter square, right? Then we'll take a part D. Yes, the sample is a cube, same 2.5 mm on a side, carrying a total current. Here in this case, current is given, total current of 0.5 amps, right? We'll check it, right? Once again, the sample is a cube. So sides are 2.5 mm and current I flowing through this cube from here. Let me assume current is flowing in this direction from this phase to this phase. So it is how much? 0.5 amps. So find out J, they are asking. Okay, how to find out with this data? So I know I, J and surface area. Yes, I can calculate now. J equal to current passing through in unit surface area, right? And if I can calculate current passing through unit surface area. How to calculate the surface area? Right, let me take the surface area 2.5 mm into 2.5 mm. If I take this is one side, this is one side, right? So we will calculate that. So J is equal to current I is 0.5 amps divided surface area 2.5 mm means 10 power minus 3, length into breadth. One side is 2.5, another side is 2, so this will give me the surface area, right? Surface area, yes, 2.5 mm cross 2.5 mm. Let me calculate this, check it. 0.5 divided by 2.5 2.5 exponential minus 3 whole square, because 2.5 exponential minus 3 whole square, it's the same thing, right? So I'm getting it as 80,000 amp per meter square. So we'll express in terms of 80 kilo. J is equal to 80 into 10 power 3 amps per meter square. Let me check it. Yes, 80 kilo. Kilo means 10 power 3. Right? Okay. The next 941. Still we can solve one more problem, I think. Okay. Well, this will be the last problem of today's class. Okay. A copper conductor, yes, in this case copper has been given. Copper conductor has a diameter has been given of copper, so 0.6 inch. So let me convert it into meters one by one. So 0.6, so 1 inch is equal to how many meters? 0.0254. You have to remember this. So diameter of the copper, let me multiply and write it, 0.6 into 0.0254. So I will write it here. So it is 0.01524. This is the diameter in meters. Then material is copper. It is length is 1200 foot long. Yes, 1200 foot. So I will convert it into meters. 1200. 1 foot equal to how many inches? 12 inches. Right? 1 foot equal to 12 inches. But if I multiply by 12, it will be converted to inches. But I should convert it into meters. So 1 inch is equal to 0.00254 meters. So just multiply, it will be converted to meters, right? 1200 into 12 into 0.0254. So I am getting it as 365.76 meters. Yes, assume that it carries a total DC current of 50 amps. Current I is 50 amps. So part A, what is asked? Find the total resistance of the conductor R. Yes, we know the relationship. R is equal to length of the conductor L by sigma S. Right? Okay. So L is known. Sigma S for copper, they have not given here. So let me take it referring sigma for copper. It is constant. We will refer it and write. Sigma for copper is 5.8 into 10 power 7. 5.8 into 10 power 7. 5.8 into 10 power 7 Siemens per meter. Then surface area, right? So it is a sphere, it is a cylindrical conductor, right? Right? Surface area means this, right? The pi r square. So we will calculate the surface area. Surface area is equal to pi r square. So pi, what is r? R is equal to diameter is given. So diameter is given d. So I want radius, d by 2. R is equal to d by 2. Radius, right? Diameter, right? So sorry, this entire thing is d. If I want r, r is equal to d by 2. Right? So d by 2 is how much? 0.01524. We have calculated 0.01524 divided by 2 whole square. Pi r square. We will calculate this. So shift pi into 0.01524 square divided by 2 square is nothing but 4. So I am getting it as 1.8241 into 10 power minus 4 meter square. Okay, I'll substitute all these things here. R is equal to L is how much? So L is 365.76 divided by, right? Sigma is 5.8. This is constant, it is given. into the surface area 1.8241 into 10 power minus 4. So we'll calculate this. So 365.76 divided by 5.8 exponential 7 into 1.8241 exponential minus 4. So I'm getting it as 0.0345 ohms, right? 0.035, they have rounded, right? That's all. 0.035, round it to next higher digit, right? Okay. The next part B, what current density exists in it? Part B, what current density exists in it? They have asked J. All these things are given. So how to find out J? J equal to sigma E. E is equal to V by L. Any other way? Current I is given. So yes, current passing through, current density is current passing through unit surface area. I want J, yes, current passing, current I is given. So J is equal to, current I is how much? 50 amps. Yes, surface area, this only, right? The surface area we have calculated here, it is there, this one. We'll take up this previous 1.8241. Already we calculated pi r square, right? So no need to calculate once again. Into 10 power minus 4. Yes, it's correct. We'll solve it. 50 divided by 1.8241 exponential minus 4. So I am getting it as 274.10 107 into 10 power 3 amps per meter square. Let me check it. Part B, 2.74 means they have expressed 10 power 3, they have expressed in 10 power 5, right? So it is correct. 274.107 in 10 power 3 amps and 10 amps per meter square. It is in 10 power 5 they are given. I have kept it in 10 power 3. If you write it in 10 power 5, you will get 2.74. Same thing, right? Next, we'll see the part C. So what is the DC voltage between the conductor ends? Means the potential difference between the two ends they have asked, right? So this end is V, this end is, so VAB, sorry, VBA or VABS, right? The potential difference we want to find out between the two ends. So which equation? E is equal to V by L we can use, but I don't know E. How to calculate E? Is it possible here? Any other way? Check it. Any other equation can we use? We want to find out. E we don't know. Yes, this is one thing. V equal to IR can I use? Yes, it is possible. No, very simple, right? So I is known, R is known. Already we have calculated. I is how much? 50 amps. It is given, right? 50 amps. Then R we have calculated already. R is 0.0345. 345. Yes, very simple, right? Why we will make our life complicated? 50 into 0.0345. So I am getting it as 1.725 volts, right? 1.725 nothing but 1.73, right? Then part D, how much power is dissipated in the wire? Power dissipated. So there are several formulas. V into I. We know V, we know I. So V is how much? 1.725 into I is 50 amps, right? So just 1.725 into 50. So I am getting it as 86.25 watts. 86.25. So 86.4 they want, right? 86.25 watts, right? Okay, we'll stop here only, or else we'll see the properties. Still time is there. Okay, so we'll stop here only. No problem. We'll stop.